Okay, hello everyone. Today we're going to be looking at ln x, the natural logarithm for x, and we're going to be looking at how we can use differential calculus concepts to be able to differentiate functions with it. Because in the real world it would be good if we had polynomials and linear equations to represent values, but that's generally not the case, and we do get more complex relationships like e to the x and ln x, the natural logarithm for x. So in this case, there are two fundamental rules that you should know about differentiating e to the ln to the x, I will be doing a video on e to the x as well though. But the first rule is that the f prime of ln x, so we have ln x as a function, and essentially f prime is just differentiating it. You should be familiar with differential calculus by now. But essentially that is 1 over x. And we take the derivative of ln x. And for the f prime of ln f of x, so we have some function of x that has the natural logarithm of that function of x, what we're essentially doing is we just have f prime of x, so we take the derivative of our function of x and we divide it by the f of x. So that's a pretty simple rule. A little hard to get your head around, but once you have got your head around, it's really easy and you can do it really quickly, which is pretty cool. So let's just have a go at doing a basic function from the left here, out this 4. In fact, that one's probably the easiest one to start with. So we have ln x to the 7 equals y equals ln x to the 7, and we want to be able to find the derivative of this function. We want to differentiate it. So the dy over dx equals, and essentially what we have here is we have an ln f of x. So what we do is we write it as being the f, we take the derivative of that function there, 7x, and from that we divide it by the original f of x as is. So we know that the derivative of 7x, when we're just differentiating any term with a coefficient of x and x, is just going to be the coefficient out the front. And of course that's because that's x to the 1, and we're bringing the exponent of 1 down to the coefficient position and multiplying them together. And that leaves x to be x to 0, which is 1. So of course we're just left with 7 as the f prime of x for that. So hopefully you can follow along with that, and we get 7 in the numerator. And now what we do is we just write our f of x as is, and that's a good thing about differential calculus. Sometimes you just get to write things as they are without fiddling. So we get 7 over 7x. And you're probably thinking we're done here, and yes, that is technically the right answer, but what we can do is we can simplify. And simplifying is obviously quite a good way to be able to represent a good mathematical answer, to be able to have something that is precise. So the dy over dx of this would just be 1 over x, and I'll show you how I got that. Essentially we have 7 multiplied by something in the denominator, and we can say that we have 7 times by 1 there if we really wanted to. But essentially what we're doing is we're just having these two terms here that cancel each other out, and that 7 in the numerator gets replaced with a 1. That's all I'm doing for simplifying. Relatively straightforward. You should remember it, obviously, from probably exponents and previous work you've done with generally any kind of fractional equations, but we get our derivative as being 1 over x in that case. And something just to remember here is that when we do have something like x to the 7 or k to the x, it will always be 1 over x. Here's a little bit of proof for you. Let's have ln k to the x, where k is any constant that we want. It can be 200, it can be a million, it can be a billion, whatever you want it to be. So you can just imagine something, some value of k in there, and to get the dy over dx, of course, it's going to be the f prime of x, and that's always just the coefficient. I explain my reasoning there. So I have k over k of x, because it's just the f of x as is. And you know, based on that, we get the dy over dx as being just 1 over x, because it's the same sort of thing here. You cross out the k's, and that gets replaced with a 1 in the numerator there as representing that value. So again, very straightforward. So hopefully it'll be a breeze just to be able to differentiate something like that, because realistically you can just use the law that that will give us the derivative of that, and you can solve it really easily just by showing the cancelling process. So it's a neat little trick and tip to be able to be aware of. So now that we've done that one, we'll move on to the next function to differentiate. And the next function, I'll just rub that one out since we've done it, we'll focus on is, how about square root x ln 4x. Now what we need to be able to do here is actually work out what kind of rules of differentiation we need to apply here. What we have here is we have an f of x term and a g of x term, because essentially what we have is we have a equation that can be solved using the product rule, and I'll make that equals y on the end now. So we just apply the product rule with our knowledge of these new laws. Essentially what you do with differential calculus is you get all these laws together and you just do the same sort of things wherever you can. You look at the entire function, you say, okay, what laws can I immediately apply here? And then you go through it and you can say, okay, well, when I get up to my g of x term and I need to differentiate that in particular, I can use those ln x terms, those ln x rules I learnt there. So really, it's just about knowing where the rules fit together to be able to differentiate. And once you sort of mastered the rules, well really, you can differentiate quite a few different types of functions. So now we get the dy over dx, again, the change in y over the change in x, the derivative, and what we do is we just differentiate the first term, and we get half x to the negative half. Again, that's simply x to the half. The square root of x is x to the half. We're bringing that down to the numerator, and the numerator we have an imaginary 1 there, so it's 1 times a half. So it's obviously half x, and then we subtract 1 from the exponent. In fact, I'm bringing it down to coefficient. I think I said numerator there before. Silly me. Anyway, we multiply that by the g of x as is, because remember we take the f prime of x and we have the g of x. So g of x as is, and then what we do is we add on the g prime of x. And what is ln 4x? Well, we have the derivative of 4x, and remember we just did it before on the board, over, and then we have 4x, so that's just going to cancel down to be 1 over x, as you know from before. And then we actually just have it times by the square root of x. And what we can do is we can leave it like that and we can say, yes, we're done, that's all good. Or we can simplify, and I'm just going to go ahead and I can show you how to simplify. Don't feel comfortable with simplifying, that's fine, but simplifying makes it look nicer, you know, it's a more elegant solution. So now what we can have is we can have this as a term, and because this is a negative indice, that's a great way to be able to simplify it, to put it into the denominator. Because of course when you move it from the numerator to the denominator, you're going to be inversing that indice. So essentially what we have is we have ln 4x in our numerator position, and when we inverse this, what we're going to have is we're going to inverse that value, and we're also going to need to inverse the coefficient. So we get 2 lots of, and then we have square root x. So it's ln 4x over 2 lots of square root x, and then we just do the same thing to the other side of the equation here. Now 1 over x is the same as having x to the negative 1. And hopefully you'll be able to recognise that based on the exponent rules that you should have learnt last year, or the year before last, or whenever you sort of learnt them. So now because of that we have x to the power of 1 multiplied by the square root of x, and essentially what that's having is we have x to the power of negative 1 times by x to the power of a half. And you know, when we have that, we need to be able to essentially simplify it based on adding the actual exponents there. So we have a negative 1 plus a half is going to make a negative half. In fact, I think I said negative half before, but that's a positive half, that's negative 1, so negative 1 plus a half is going to make a negative half. So we can rewrite that entire thing as being 1 over square root x, because it's essentially x to the power of negative half, and again when we put the negative half into a denominator over 1, it's going to be a positive half. And again, it just makes it slightly more elegant than having, say, this kind of thing. However, if you want that kind of thing, and you can work with that kind of thing in a question, then by all means, I guess there's